All right. Good morning, everyone. So we'll get started here. So let me begin with again some reminders items here. So homework 6 will be due tomorrow night by midnight. Okay, so make sure you finish them by midnight tomorrow. Um, Also, another reminder here, I would like to ask you guys to come in to make up your missing labs this Friday. Okay, so this is on Friday only. Okay, so if you are in a Wednesday section, you can also come to the Friday to make up your missing labs. Okay, otherwise you can wait until the last 2 weeks of the semester. So you will have two chances to make up your labs on Wednesdays. Okay. So that's the lab for this week because we don't have school on Wednesday, so we will not meet on Wednesday. Okay. Um, then the last one is the exam number 2 will be coming up next week. Okay. So again, for Fridays, in-seat attendees, you are taking exam on Monday next week. Okay, to be in the physical classroom in seat this time. Right. And then for Wednesdays, you guys are taking it on Wednesday. Okay. All right. So today we'll be looking into chapter 7 on work energy. All right. So mostly like work energy and work energy relations here. And we will touch on a little bit of energy resources at the end of this chapter. All right. So to start with, we'll look at the definition of work here. For the scientific definition, I mean, in our daily life, we have used work, the term work a lot. Like we say homework, housework. You are working a lot, okay? But that's not a scientific definition. So in science field, work is defined as the force, all right, multiplied by the displacement that is parallel to the force. So if you are pushing a box in one direction, in this case, in the figure shows here in the horizontal direction, then the box moves in the horizontal direction as well. Then you multiply the force and then the distance it has moved. Okay, so that gives the work. Um, SI unit for work is newtons times meters coming from the two quantities, the force and the distance. All right. And then it has its own unit as well called joule. So 1 joule is equivalent to 1 Newton times meter. Okay, so it's Newton times meter. All right, so that's the scientific definition for work. All right. Um, you don't always have the force and then the displacement in the same direction necessarily, right? So for example, if you are in the airport pulling your suitcase, so it's unlikely you are going to pull it horizontally, right? You are going to pull it at one angle with the horizontal. So then your force is in one direction, your direction is in a different direction. Your displacement is in a different direction. So in that case, then you can actually resolve the force into two components. One component that's parallel to the displacement, and then the other component that is perpendicular to the displacement. Okay, so then the work done by this force is only coming from the component of force that's parallel to the displacement. So it's the F cosine of theta times the displacement d. Okay. And you can also rewrite it as FD cosine theta. So that means you can actually do the other way around. You can resolve the displacement into two components. One component to be parallel to the F direction of the force, and then the other component to be perpendicular to the direction of the force. Okay, so it's the only direction that force is parallel to the displacement that does work. The direction that force is perpendicular to the displacement, then it does zero work. Okay, so that's another way of to. This is the in general they work by a force. So it's going to be force times d times cosine theta. Okay, and then you can write this general form because it includes the special form we talked about earlier when the two are in the same direction. So then theta is equal to 0. So cosine 0 is 1. Okay, so in the special cases, if theta is equal to 0, then you write down FD cosine of 0, which is equal to FD. Now, in the case if force is perpendicular to the displacement, then the angle theta is 90 degree. Okay, so then you are doing FD again cosine of 90 degree, which cosine of 90 degree will be 0, right? So then work is equal to FD times 0, which means the force in the perpendicular direction to the displacement actually does 0 work. Okay, and then this is the general form FD cosine theta. Okay. That's another way of if you resolve displacement into the two components. Okay, so then you can do F times parentheses D cosine theta. But in general, just write down FD cosine theta. That should be fine. Okay, so let's take a look on a quick example here. So this one says if a 57 kilogram packing crate is pulled with constant speed across a rough floor with a rope that is at an angle of 37.0 degrees above the horizontal. If the tension in the rope is 142 Newton, how much work is done on the crate to move it 6.10 meters? Okay. So give it a try. I think it's should be it could be more clear by saying how much work is done by the tension force. Okay, by the tension on the crate. All right, so give it a try, and then we can take a look on the solution in a couple of minutes together. Okay. All right, I think we can take a look at this together now. I saw a few responses in already. So if you are pulling a crate by a force, tension force in a rope of 142 newtons, okay, and then this guy moves by D equals 6.10 meters, all right. So we are looking for the work done by this force only. Okay, so you can just focus on this guy. Now the rest, there will be friction force on the crate in that direction. There will be normal force upward, weight downward. Okay, but we don't have to care about them. We are just need to find the work done by this force over here. So then you can write W equals to FD, okay, cosine of theta, because this is a horizontal direction. The crate will move in that direction. All right. So then you simply will be just plugging numbers here in this case. All right. Make sure you take cosine instead of sine. All right. So then this gives you 692 joules. Okay. I see from your responses that you submit, you got this right. Okay. So good job on that. All right. Any questions you guys might have? Okay. So then if now we can move on here. All right. So because work is equal to force times displacement times cosine theta between the force and then the displacement. So then you can see depends on the angle the two vectors makes, the force vector and displacement vector make. If the angle is in the range of -90 to 90 degrees, which cosine of that range for the angle gives you positive number. So then work will be positive in that case. All right. If the force and displacement are perpendicular to each other, so then theta will be either positive 90 or negative 90. In that case, cosine of 90 degrees, positive or negative, they are both equal to 0. So then work is 0. Right. And then now force could be in with the displacement in the angle that has a range of 90 to 270. Okay, so that means the component of force in the direction of the displacement will be opposite to the displacement. So then in that case, the work could be also negative. Okay, so just keep in mind because of the angle, cosine of the angle has different ranges or different values, could be positive, could be 0, or could be negative. So then what could be positive, could be 0, or could be negative. Depends on the angle. Okay. All right. So in the case if you have multiple forces on the object, for example, in this case here, the car drives down the slope. So there will be normal force, there will be the weight, there will be friction force or air resistance force here. Okay, so the three forces are indicated in red arrows here. Now the displacement is in this blue arrow here. Okay, so then in that case, you can find the total force first by adding those three vectors or three forces up, but doing this in vector format. Okay, so because those are vector quantities, and then do the F total cosine theta. Okay, so this again, theta will be the angle between the total force and then this displacement vector. Okay, or you can do work done by each of these forces individually. So then you have three works from each of these three forces. Okay. And then you can add the work up. So in that case, the work will be a scalar quantity because work doesn't have direction. So then you can do it that way too. Okay, so either way, they should give you the same result. Okay, so either figure out the total force first or figuring out each work individually by each individual force and then add them up. Okay, you'll get to the total force either way. All right, so that's the definition on work. And the next section, we'll be looking at the kinetic energy and then work energy theory. All right. So I think it's quite straightforward that if, so in this case, we can see that if an apple falls down from the tree, right? So then the speed increases, right? Because it's under the apple is under the influence of the weight here going in the direction downward. Now its displacement is also in the downward direction, right? So then you can see if they are in the same direction, the force and then displacement, they are in the same direction. So then work done on the apple is positive, okay? So when work is positive, then speed increases, all right? On the other hand, if you throw a apple upward, right? So then due to the gravity here, doing work on the apple here, the gravity is in the opposite direction of its displacement. So then negative work is done on the apple. So the speed of the apple decreases, right? So it's straightforward that we can come to this conclusion here. When positive work is done on the object, then its speed increases. Otherwise, when the negative work is done on the object, then its speed will decrease, okay? So by knowing that, let's take a look on some algebra here. All right. So to start with, I'm going to make some assumption here. So suppose the initial speed of the apple is vi, it's called vi, and then the distance the apple travel, I will call it d. You can do position final minus position initial, okay, to get the distance. And then I'm going to assume its speed increase to final speed of VF, okay? And then the total force on the apple, I'm going to just say total F total, okay? So you can imagine if we consider the air resistance here, then total force should be equal to the weight minus the air resistance, okay? If we do not consider air resistance, then total force will be just the mg, the gravity, okay? But I'm going to just say either way, it's going to be the total force, okay? So let's take a look at some algebra over here. All right. So to start with, we'll apply Newton's second law here. So Newton's second law says total force is equal to mass times acceleration. All right. So then we can rewrite that acceleration should be equal to total force times the mass. In this case, the apple is just moving in one direction. Okay, so it's one-dimensional motion. And then you can take a look on the equation of motions for one-dimensional motion, assuming the total force is not changing. So then you'll have constant acceleration. Okay, so if you remember, there were 5 equations of motions for one-dimensional constant acceleration motion. I'm going to just pick the last one, which it says the final velocity square is equal to initial velocity square plus twice acceleration of the x minus x naught, right? Which is d here. Okay. So then I'm going to replace the acceleration with the force total over the mass. All right. And then check on this equation again. So then I will see that final velocity square should be equal to initial velocity square plus 2 times F total over the mass times the distance. Okay. Now, if you look at the second term on the right hand here, look on the F total times distance, right? So then this would be the total work on the apple, right? Down on the apple, because you have force total times displacement, which gives you work, okay? Or work total if you want. That equals to F total times displacement, okay? So then V final score equals to V initial score plus 2 times work total divided by the mass, okay? So I'm going to multiply both sides of the equation by the mass, and then this by the mass. So then I will have mass times final velocity square equals to, so you'll distribute mass into the 2 terms inside the parenthesis. So mv initial square plus this m and this m will cancel out, twice of the work total, okay? And then I'm going to divide both sides by 2, or multiply both sides by 1/2. 1/2 to this side, and then also 1/2 by on this side. So then it's going to be 1/2 mv final score equals to, again, you distribute 1/2 into the two terms inside the parenthesis. So 1/2 mvi score, okay? And then 2 times 1/2 will cancel out plus work total, okay? So then I can put this guy in this side of equation. So it gives me 1/2 mv final score minus 1/2 mv initial score. That should equal to my total work done on the apple, okay? So then we arrive at this conclusion over here. So 1/2 of the mass times the final velocity minus 1/2 of the mass times the initial velocity equal to the total work done on the apple, okay? So let's go back to the slide, okay? Which on the next slide, so it's the previous ones is this guy here. When we did this algebra on the paper, then we came to this conclusion: the total work done on the object is equal to 1/2 mv final square minus 1/2 mv initial square. Okay, so in this case, you can see the total work done is equal to a quantity here that is equal to 1/2 mass times v final square, right? And then minus 1/2 mv initial square. So we are going to call that 1/2 mv square to be the kinetic energy of the apple, okay? So it's basically proportional to the mass and then proportional to the speed square, okay? So by given this definition, then we can relate the work done on the apple to the change of its kinetic energy, because now we have final kinetic energy minus the initial kinetic energy, okay? So this is the work energy theorem. It says, basically it says the total work done on an object is equal to its change in kinetic energy, okay? So total work equals to change in delta K, which K stands for kinetic energy, all right? That's equal to 1/2 mv square minus 1/2 m initial square, okay? So this is the work energy theorem. Now, from the equation, you can kind of see that because work has a SI unit of joules, so then energy should also, or kinetic energy should also have a SI unit of joules, okay? All right, I think it's not in the slides, but kinetic energy should also have the same unit as the work, okay? Because they are equal to each other, all right, dimension wise. So dimension of work should be equal to the dimension of the kinetic energy. Let's take a look at a couple examples here on work energy theorem. All right, to start with, we are going to look at this first one here. It says, if there's a picon falls 60 meters to the ground, where the picon has mass of 0.14 kilogram, and it lands with a speed of 30 meters per second. Okay, so it's asking you, with what speed would be the picon have landed if there had no air resistance? Okay, so that indicates that the 30 meters per second is the result of encountering the air resistance. Okay, so if you have no air resistance, then you should expect to have more than 13 meters per second for your landing speed, right? And then B says, did the air resistance do positive, negative, or zero work? Okay, so let's take a look here. So this one doesn't necessarily is related to work energy theorem, but I think more when it says if we consider no air resistance, then we can just use what we learned earlier, the kinematics, to figure out the speed. Okay, so you guys can give it a try, and then we can take a look in this in a couple of minutes together. Okay. All right, I think I'm getting responses in. I wait for another 30 seconds or 1 minute, and then we can take a look at the solutions together. So if you have finished this one, you can go to the next slide. There's continuing questions in the next slide. You can work on that. All right, so let's take a look here together on this one. So the PyCon falls down here. It's assuming that no air resistance. No, that means the oscillation is equal to gravitational oscillation 9.80, right? It says distance travel is 16 meters, and then initial velocity, it should be starting from rest. Okay, so initial velocity should be 0. We are looking for the final velocity here. So again, this is one-dimensional constant oscillation motion. You can look at the equations of motions that we learned beginning at the beginning of the semester. So looks like the easiest one to apply here will be the V final equals to V initial square plus 2A times D. Okay. So then V should be equal to square root of initial square plus 2A times D. Okay. Distance travel. So then initial is 0 plus 2 times 9.8 times 16 meters. Okay, that should give you 17.7 meters per second. Okay, or if you want, you can keep to sig figs. Okay, and B here is asking you now if we consider the air resistance. So would the air resistance do positive, negative, or zero work? Explain why. Okay. So if less air resistance, so you can see that on the PyCom, if it falls down here, there will be mg, right? The air resistance will be in this opposite direction to the velocity. Okay, it will gain velocity in downward. So that means displacement is in that direction. Okay, velocity is having the same direction as the displacement then. So these two are in opposite direction. Okay, so then work done by F resistance should be negative. Okay, should be negative because they are the air resistance force and then the displacement are in the opposite direction. Okay. All right. And I think most of your responses are correct. Okay. Yeah, except one. There's yeah, I think the last one here says 11.83 joules. That might refer to the next one. Okay. Okay. We'll take a look on the next one here. Okay. So let's go to the next slide. So this is continuance from the previous problem. Okay. So now it says in the previous problem, how much work is done on the PyCom by the air resistance. Okay. So because we just learned that work today, we learn, I think, pretty much two things here. So work is equal to force times distance times cosine theta, right? And then the second thing we learn is total work is equal to change in kinetic energy. So Kf minus Ki. Okay, so that is pretty much the two main things we learned today. But let's take a look. What we are looking for the work done by the air resistance here. All right. So then work done by air resistance, or you can say work sub air. So that should be air resistance force times the distance, right? Times cosine of the angle the two makes. So as I mentioned earlier, so PyCon falls down here. This is the displacement. This is the air resistance. Okay, so they are in opposite direction. So this guy is 180, cosine of 180. So it should be negative, should be a negative number. Okay, we know that D is 16 meters, but the question is what's air resistance here? Okay, so in this case, the air resistance is not given, and you can expect that as the resistance should be a changing force, right? Because um, air resistance is one of the drag force we learned in chapter 5, I think. So then it's proportional to the speed or speed score, okay? Depends on what type of the air resistance you have. So we can assume it's proportional to the V score. So then you can see the speed V is changing, so then the air resistance should be also changing, okay? So you are likely not able to use this equation, okay, because this is varying force is not given, okay. So then we should turn to this guy that we learned today, okay. So we can take a look here. On the PyCon here, you can see there's mg less this F of air, okay. So two forces on the PyCon. So then work should be done by these two forces, all right. So again, because this guy is varying, so you probably couldn't be able to use the total force times distance, because total force then due to air resistance is changing, so that should be also changing. Okay, so but you can do work done by this guy and then work done by that guy. Okay, so then you can say work total then can be calculate or can be equal to work done by gravity plus work done by the air resistance. Okay, or F or W sub air. All right. Now also this, the work total is equal to kinetic energy final minus kinetic energy initial, right? So the kinetic energy is equal to 1/2 mv squared. We know the initial velocity is 0. We know the final is given as, in the previous problem, is given as 13, right? So we can calculate that. So then work total can be calculated by taking the difference of the kinetic energy final and initial, right? And then this guy, work done by gravitational force, should be calculated because gravitational force is a constant, then the distance traveled is known. So that can be calculated, okay? So this can be calculated, this can be calculated. So then this can be solved, right? Without knowing the actual air resistance force, then you can calculate the work done by that one, okay? So this is what we are going to do. You can calculate, you can plug in the numbers here, calculate that, and then take the number down here. You can calculate this guy. Work by G should be equal to mg times the distance traveled. Mg is the force, the weight, and then distance is displacement, okay? And then take the number inside here, you can solve for that, all right? But I'm going to set this equal to that. So the right-hand side of the equation here equals to right-hand side equation there, okay? And then I can calculate work done by this guy, okay? So then I set up work by gravity plus work by air resistance should be equal to Kf minus K initial, which means K or 1/2 mv final minus 1/2 mv initial square. Okay, so that's Kf Ki, Kf Ki. So initial speed is 0, so that means this term is 0. Okay, so then my work done by my air resistance should be just 1/2 mv final square minus this guy, which is mgd. Okay, this is mg d for the work done by gravity. So then minus mgd. Okay. So then I can plug in my numbers here. M is 0.14. V final is 13 meters per second square minus 0.14 kg, 9.8 meters per second square times the D, the 16 meters. Okay. So by doing that, I end up with a work of negative 10.12 joules. Okay. So you can calculate the work done by the air resistance this way. Okay. If you don't know the air resistance force. Okay. So this guy here. All right. So this is part A. Any questions you guys might have? All right. So if not, then the second part says, what was the average force of the air resistance exerted on the PyCon? Okay, so it's assuming if the air resistance is an average force, so then that means you can treat it as a constant number. Okay, so again, if that's the case, then work done by air resistance should be equal to F air times D, right, times cosine of 180 degrees. Okay, so which is -1. Cosine of 180 will give you -1. All right, so then that will be equal to minus F air times minus F air average. I should say that way. Put a bar on top to indicate its average. Okay, times D. All right, so we can set because we calculate this work done by air to be this guy, so we can set this to be equal to that, okay? Or you can say this is equal to the air, work done by air. So then my average air resistance force should be equal to minus our work done by air divided by the distance travel, okay? So minus 10.12 joules divided by 16 meters, okay? So then that gives me the 0.63 newtons, okay, as my average air resistance. Okay. Any questions you guys might have? All right. So if not, then we can move on here. So so I think in the beginning we talked about work done by constant force. So then you do work the force work equals to the force times the distance travel times cosine theta. And in reality, there might be scenario that the work or the force on the object might be a changing force. So for example, the one we checked earlier, air resistance force is proportional to the speed square. So it should be, in reality, it should be a varying force, okay? Or in the other cases, like if you are having a spring, you pull the spring, if the spring is stretched by different amount, then the force in the spring is a varying force as well, okay? So in general, if you have a varying force, okay, you can do a graph, or we can look at the constant force first. Okay, so if it's a constant force, then if you plot the force of cosine theta, which means the component of force in the displacement direction. Okay, so plot F cosine versus D, then you can see work is equal to FD cosine or F cosine times D. So then that's actually equal to the area under this rectangular area. Okay, so that means if you plot force cosine, That's the curve there. So it's the area underneath the curve. Okay. Now, similarly, if you have a varying force, for example, it varies with distance of distance travel, the force that is linear response to the distance travel. So then it's a changing force. Okay, in that case, you can actually divide this area here into many small pieces, rectangle here. Okay, so then you can do the same thing, and then you can add them up. Okay, so it turns out you can do this in calculus form. Okay, but if you haven't learned calculus, that's fine. So it's again basically it will be the area underneath the curve if you are going from one position to another position. Okay, so that means the um, change in displacement. Okay, or change in position. All right, so it's again it's the area underneath the curve. Okay, so either way, if you have a constant force, if you have a varying force or variable force, then if you plot force times cosine theta versus the displacement, the work done is going to be equal to the area underneath the curve. Okay. A special case for variable force or varying force is the spring force. Okay, so you can stretch a spring by an amount of x, so then force equal to F equal to kx. Okay, and then in that case, force and x are in the same direction, so then F cosine will be just F. Okay, because theta will be 0. So then if you plot force versus x, the displacement, then the work done will be under that area of curve. So if it's being stretched to x, then it's over here. Okay, so then it's the area of this triangle here. So the area for the triangle should be 1/2. This is the right angle triangle, so it will be 1/2 of the one side of the right angle here multiplied by the other side. So 1/2 of kx times x, right? So it gives you 1/2 kx squared, right? So then in that sense, the work done by a spring, if you are stretching it, it's going to be equal to 1/2 kx squared, okay? Similarly, if you compress a spring, okay, then it's also going to be 1/2 kx squared, okay? So in that sense, because in that sense, you are doing minus x squared. If you take the compression as minus, then but if you do the square, then minus will become positive. Okay, so either you are stretching a spring or compressing a spring, the work done is equal to 1/2 kx squared. All right. Now let's take a look an example here. It says initially sliding with a speed of 4.1 meters per second, a 1.5 kilogram block collides with a spring and compresses it 0.27 meters before coming to rest. What's the force constant of the spring? Okay. So, so for this one, because the force on the spring, you can see it's going to be a varying force because your compression of the spring, although it says 0.27 meters, but that's the final compression, right? So as the block collides with the spring, then it starts to compress the spring from 0 to 0.27 meters. So you can see the stretch of the spring is varying over the course. So then the force should be varying also over the course. Okay, so so you can you have to use like what we just learned earlier. Okay, so for the spring force, you cannot do work equals to force times x, but for a spring, it's going to be 1/2 kx squared. Okay, and then I think you can apply work energy theorem here to look for the spring constant k. Okay, so give it a try. I think I'll give you guys 2 to 3 minutes on this, and then we can take a look on the solution together. All right, so let's take a look here together. So you can see when the spring start to be in contact with the block, start to have contact with the spring here. So at that moment, it says initial speed of the block is 4.1. Okay, so you can see as this block is pushing the spring in that way, so compressing the spring, you can see the spring will start to have a force, spring force on the block. Okay, in that way. So the force now vertical direction, normal force and weight will cancel out. Okay, so the only force that matters here is the spring force on the block. Okay, so the force on the block is in that direction, but the block keeps moving in that direction. So force and then displacement, they are in opposite direction. Okay, so you can see that now the spring start to do negative work on the block. Okay, so then the speed of the block will decrease, and then at a certain point later on, when it reaches the maximum compression, this block speed reduced to 0. Okay, and then that compression is 0.27 meters. Okay, so in this case, we can take the block as our object of interest. So then we can apply work energy theorem on the block. So W total on the block is equal to 1/2 mv final score minus 1/2 mv initial score. Okay, and then given that the spring force and then the displacement of block that are in opposite direction, we can know that work by the spring is going to be negative. Okay, so it's going to be negative. So work by the spring is 1/2 k x squared. Okay, so negative of that equals to this minus that guy. Now initial speed is 0. Okay, when it reaches maximum compression. So then this is minus 1/2 mv initial score. Okay. So then you can see that minus 1/2 and minus 1/2 can cancel out, right? So you are looking for K, and then everything else is given, right? So you can solve for your K from there. So K then should be equal to MV initial score divided by X score, okay? So M is given as 1.5 kilogram. And then the initial speed is 4.1 meters per second square divided by 0.27 meters. Okay, do not forget to square that. That gives you the K constant as 346. If everything is in SI unit, then this should be also in SI unit. Okay, or you can take 2 sig figs here. So 3.5 times 10 to the second meters per sec, newtons per meter. Okay. Um, any questions you guys might have? All right. So if not, then we'll stop here for today. So remember on Wednesday, you guys have a break, so we don't meet on Wednesday, but we'll meet. I will meet you guys on Friday. Okay. So see you guys on Friday, and then don't forget to finish your homework number 6 by tomorrow midnight. Okay. See you guys.